Hi guys! I decided to make a video about batteries to discuss some of the most important topics for a Onewheel. What I want to cover is voltage sag, what is it and why do we care? I want to talk about how to pick the best cells for your pack, then talking about battery pack configurations. We'll talk about the VESC firmware and how to configure it, and then some popular questions that I want to answer directly. So let's start with voltage sag. What is it? It is a temporary voltage drop caused by load on a battery. When a battery is under load, meaning that there is current flowing, the voltage will inevitably sag. This sag increases as the battery current increases. Doesn't matter what the motor current is, it matters only what the battery currents are. So, as I said, it's temporary. So when the current stops, the voltage will go back up, obviously minus whatever capacity has been used. Why do we care for our Onewheels? For us, sag will limit the usable range of our battery. The higher your typical or maximum currents, the sooner you'll feel it. So heavier riders are more likely to be affected when you're on steep terrain or off-roading or soft ground. You will also need more currents and are more likely to feel sag. So how do we notice it? Let's look at an example here. We'll assume a 12S battery pack at 50% charge, which according to conventional wisdom is 44.4 volts. We assume a very short 30-foot long ride, and when you now start riding your board, the voltage will instantly change. On a flat road, it might be just like 43 volts instead of 44. If you're going on a steep uphill instead, it might drop down to like 40 volts. And on a downhill, it will increase to 45. But when you stop riding your board, the voltage will go back up. And if the section was short enough, the voltage might even be back to the original 44.4. So how do we prevent it? Typically, we just need a better battery. It starts with the battery cells. High discharge cells, 20 amps or more, will sag less given equal current. But remember, high capacity cells are usually not also high discharge cells. Typically, the highest discharge cells will have moderate capacities, but in the end, you'll get better range with them. So don't look at capacity, look at the discharge rates. Obviously, when putting multiple cells in parallel, you can reduce sag because the load is distributed across the cells. The cell current gets divided among the number of cells. Now, if you run some massive 12S5P battery, then high discharge cells aren't even a must because the load is split across so many cells that each cell is fine being rated for 8 amps or 10 amps. You can still do 50 amps in total. That's what many cheaper e-bikes do. They use bigger batteries, but they put really cheap cells in it. Now, on a DIY Onewheel, it's pretty hard to fit more than a 2P pack. Some boards even use just 1P packs, like Float Wheel's default battery is 12S1P. So in that case, high discharge is the top priority for maximizing performance and range. Voltage spikes, they're the opposite of sag, pretty much the same thing, but in reverse. During braking or going downhill, the negative currents that are caused will temporarily increase your battery voltage. So a fully charged battery can temporarily exceed 4.2 volts per cell when you're braking or going downhill. Here also, high discharge battery packs will produce less severe voltage spikes. So before I talk about the VESC configuration, I want to talk a little bit about lithium-ion batteries and operating voltage. There's plenty of videos about batteries and how they work and all the details. I'm by no means an expert. I've picked all this up since last year when I started building my Onewheel. But here is what I've learned. So lithium-ion cells are typically safe to operate when their charge level is between 3 and 4.2 volts. So for a 12P pack, that's 36 volts to 50.4. Temporarily, the same lithium-ion cells can go beyond that range. So sag can easily take us down to 2.8 volts without causing any instant damage. Also, voltage spikes due to regenerative braking can take us up to 4.3 volts without causing instant damage. Of course, long-term battery integrity can be affected. The further you exceed the recommended voltage range, the more likely you will cause permanent damage to the battery cells. The more often or longer you exceed the recommended voltage ranges, the worse it is for your battery. But do you really care if your battery needs to be replaced after 3 years instead of 3.5? I personally don't. So now let's talk about the VESC tool. We want to configure it, prioritizing rider safety. That obviously is the most important thing. We also want to maximize the range that we can get, and we want to protect the battery. Pretty much in that order of priority, at least for me. The VESC firmware includes a few relevant settings. First, it has alerts with low voltage and high voltage tilt packs, and it has limits, meaning voltage cutoffs, which should be a last resort, and current limits. So let's talk about those in detail now. So to configure the VESC firmware, the first step is to set your voltage cutoffs. Those really protect the battery by triggering a nosedive, by the way. So it's not for protecting the rider, it's for protecting the battery. There's a cutoff start, when to start reducing output currents, and a cutoff end, at what input voltage will the current be reduced to 0. So reasonable values for a Onewheel would be to set the cutoff start and end to about 2.8 down to 2.6 volts per cell. Yeah, you may argue this is really, really low, but keep in mind this is just for temporary voltage drops, not for constant charge levels. But we'll talk about that in more detail later. So these are the values that I personally use, and for a 12S battery that produces about 34 volts for cutoff start and 31.5 for cutoff end. But remember, we don't plan on ever triggering those cutoffs. They're just a last resort where you're protecting your battery because you've ignored the alerts that came before that. And now let's talk about those alerts. So how do we prevent nosediving from low voltage cutoffs? We use low voltage tilt back. In the VESC tool in balance tilt back, we have a low voltage tilt back setting. So we want to set that to something around 3 volts per cell, which is about 2 to 3 volts higher than cutoff start. So in the VESC tool, it looks something like this, and 37 volts is what I would recommend for a 12S battery. Now, we've set it to 37 volts, but expect to hit the tilt back when your unloaded voltage is around 42 because of sag. Right? The weaker your battery is in general, the more it will sag. If you weigh more, it will happen earlier as well. You might already start feeling tilt back when the battery is at 44 volts if you're heavier, or if you're using a weak battery, like for example the default float wheel battery. So what do you do once you have hit the low voltage tilt back and you still need to get back to your car or back home? The best bet is, if you want to avoid carrying your Onewheel, go slow. That uses less currents. Try to avoid inclines. That really keeps your currents minimal. But sometimes you can't avoid it. I have a steep driveway. If I arrive in front of that driveway with a nearly empty battery, I kind of have to carry my board up there. It has happened several times already. Also, you got to remember that performing the actual tilt back requires extra current. which increases voltage sag. That's why you need a buffer between the tilt back and the cutoffs. You don't want to set your tilt back to just 1 volt above the cutoff. Otherwise, the act of performing tilt back will take you right into cutoff zone, and then you got a cutoff with tilt back. That's not what we wanted to achieve. Another thing to do is to prevent the battery from overcharging. There is no simple answer to this. If you live in a place without hills and you're a light rider, then you're in luck. It will not affect you much. But if you do have hills to deal with, then you've got to be very conscious of the state of charge of your battery. You want to avoid going downhill when your battery is full. Also, you might want to try limiting your charge level to something that's below 4.2 volts per cell. But keep in mind that a standard BMS only starts balancing once it gets above 4.1 volts per cell, so you don't have too much wiggle room there. Also, if your battery is full but you have to go downhill, then try to go really slow to keep those regen currents from breaking to a minimum. Again, the VESC firmware has a high voltage tilt back setting in balance/tilt back. So you want to set it for spikes, not for resting voltage. I recommend around 4.3 volts per cell. You got to be careful though. You have to be mindful of your BMS's high voltage cutoffs. So if your BMS has a high voltage cutoff, then you should be below that level. So what it looks like in the VESC tool, I have 52 volts set for my high voltage tilt back for a 12S battery, and this has worked pretty well for me. If you are on a full battery, do expect to hit high voltage tilt back when you go downhill. The same happens if you are on a full battery, you leave the house and you do an emergency brake, you will be dragging your tail, so be ready for it. Now, the last configuration value that people might notice in the tool is current limits. Obviously, if you keep your currents lower, you will also keep your voltage sag and spikes lower. But it's not really a good idea to do this because the current demand is really driven by rider weight, riding style, and terrain. So if you're limiting currents on a balanced vehicle, it may reduce the vehicle's ability to balance. And the VESC firmware does not allow limiting continuous currents versus spikes. So any limits that you set will primarily affect your spikes, meaning the short bursts that you need during braking. And instead of now slowing down, you're going to drag your tail, start losing your balance, and crash in the worst possible moment. So limiting currents is not really a good idea. Also, a battery rated for 10 amps can still easily handle 20 to 30 amp spikes. It will probably respond with insane voltage sag, but still that's better than an artificial cutoff by the software. Also keep in mind that you can't feel voltage sag as long as your battery is full. So do you really want to protect the battery at the expense of your own safety? To me, the answer is pretty obvious. I'd rather avoid ending up in the hospital than increasing the battery life. I can easily build a new battery if I have to. Now it's time for frequently asked questions. First one, can a 13S battery destroy a VESC that's rated for 60 volts? The answer is yes, in theory. A fully charged 13S battery could potentially spike up to 60 volts or above, given sufficiently high regenerative braking currents. But if you use high discharge cells in a 2P configuration, it is very difficult in practice, according to my observations, and I analyzed tons of logs in detail specifically about that. It's very hard to get above 2 to 3 volt spikes. So there is plenty of margin left even with a fully charged 13S battery. I have personally been running 13S 2P on a cheap Fokker for more than 4 months. So all in all, I would say if you use a 13S 2P with good cells, you'll be fine.
How do we maximize range? Can I get more range with the highest capacity cells? The answer here is unfortunately no, unless those cells also have a 25 amp plus rating, which they typically don't in my experience. Because Onewheels use 1P or 2P battery configurations due to limited space, the discharge rate is a lot more important than capacity for usable range. So those claimed 3,500 milliamp hours might give you a benefit, but only if you plan on riding at a constant low speed on flat roads. And I put the Energizer Bunny there because that's how the capacity is measured. If you have a low current, 1 amp or below, that's when you can actually get this type of capacity. But what happens is that if you use low discharge batteries, they'll become unsafe to ride once they hit 50% charge. So only the first 3,500 milliamp hours of a 2P pack will actually be usable. Therefore, a 50 amp 5 amp hour pack will always beat a 20 amp 7 amp hour pack when it comes to range, and obviously also in performance. The next question is about sag. Here we want to compare an 18S 2P versus a 12S 3P pack. Which configuration will have more sag? Obviously, let's assume to keep it apples to apples, we'll assume the same 25 amp rated cells in both packs, and we'll assume that the VESC that we have can handle 18S. If you cannot handle it, then right, what's the point? Now, both configurations require 36 cells, so we'll have the same watt-hour capacity. 12S3P can handle 75 battery amps, 18S2P can handle only 50 amps. So if you draw the same current, for example 20 amps from both batteries, then obviously the 12S3P will sag less because the same current is now spread across 3 instead of 2 cells. But assuming equal current is the wrong way to look at this. We should compare sag assuming equal wattage. With 18S, you need 33% less current than with 12S to produce the same power. So your VESC will draw much lower battery currents with an 18S battery when you're doing the same speed and the same type of maneuvers. So the real answer is that the effective sag is roughly equal, and because of that, I would say that an 18S 2P is the smarter choice if your VESC can support it, because it gives you a larger headroom in terms of duty cycle. You can go faster, you don't have to go faster, but if you're going 15 miles an hour and you hit some big speed bump or something, you don't have to worry about being close to the duty cycle limit or hitting tilt back. Whereas with a 12S battery, you'll be riding near the limit a lot more often, even if it's 3P. The last question is about side effects of sag, and what if you don't care about range? Does sag really matter? The answer is, it does matter if you like going fast. If you assume a 12S battery at 50% charge, so 44.4 volts, and assume that your top speed is 15 miles an hour at 75% duty cycle. Now, if you hit a speed bump or a pothole, your motor current will spike, let's say 60 amps, which is not unusual. And at that speed, your battery amps will also spike really high. So 40 amps is not unrealistic. Now, a weak battery with crappy cells or 1P configuration can now easily sag 10 volts or more. And if you take your starting voltage of 44 and you subtract 10, you're at 34. Now, the duty cycle will exceed 90% due to the reduced input voltage. Tilt back will kick in. That adds further demand on current. And 34 volts is cutoff territory, so a nosedive is very likely here. Bottom line is, if you're riding a Onewheel, you always care about sag, so there's no way around high discharge cells. I hope this was helpful. If you guys have any questions, put them in the comments. But also, if you join the Funwheel or Floatwheel Discords, there's lots of knowledgeable people there. You will get the information you need eventually. Thanks for watching, and see you guys next time.